Okay. All right, number 3 says that we are looking at y equals 2/3 x squared plus 1 to the 3 halves. Find the arc length of the graph of the function over the indicated interval. So did it show up on the copy? Can you guys tell what the indicated interval is? 0 to 1. Yeah, so the 2 is the y coordinate. The x coordinate would be 1. So we're going to do 0 to 1. So we're going to find the arc length of 0 to 1. And I'm going to go ahead and write down just the function itself. So we've got 2/3 x squared plus 1 to the 3 halves. And then if you look at your notes, we're doing the interval from 0 to 1. If you look at your notes, this is the formula. So we have the interval from 0 to 1, and we have to do the square root of 1 plus, and what does this notation mean? What does that mean? The derivative squared. So, no, you're right, you were just reading it in the notation. So let's go ahead and let's find the derivative so that we can plug it into that formula. So if that's y, then how would we find y prime? Okay, so I'm going to do 2/3 times 3 over 2, so that's why Michaela didn't have any coefficient in the front, because she was thinking that those automatically canceled out. No, you're good, you're good. I was like, wait, why didn't she have any coefficient? Mentally, because it already canceled out. So x squared plus 1 to the, wait, what's the exponent? 1/2. And then times 2x, because we're doing the chain rule. Okay. So there's our derivative. So we know that the 2's canceled, the 3's canceled, so our coefficient there is gone. Okay, so now we're going to go ahead and use our arc length formula. So the arc length is the integral from 0 to 1, square root 1 plus, and then we're going to have the derivative squared. So we're going to have x squared plus 1 to the 1/2 times 2x, my parentheses were too big, squared. Okay. And then for today, we'll go ahead and just plug these into a calculator, knowing that it is possible that somewhere these could, if these were reasonable at our level of understanding to do by hand, that they could at some point give this to us as a multiple choice problem, not an effort, or like a calculator inactive multiple choice problem, make us do it by hand. Or it could be calculator active like this. So math 9, 0 to 1. I would say everybody should definitely be typing this in because this is a doozy of parentheses. If you want to avoid some of the parentheses, you could certainly type in your derivative into your y equals and then use that, and then you could avoid some of those parentheses. So I'm getting 5/3. If you were to type it into your y equals, then you could do x squared plus 1 to the 1/2 times 2x, have that plugged into your y equals. And then when you did your integral, you would just have to do 0 to 1 and then square root of 1 plus, that was almost a brain fart, that squared. Now you have way less parentheses. It's a little bit easier to type. Same thing. So if you want to utilize your y equals screen to help you have an easier time typing things that are going to use a lot of parentheses, that's a good way to double check answers, especially on FRQs or on multiple choice problems that you are not sure of. Some multiple choice problems are going to be easy, but if you're running into one where the parentheses are really giving you a hard time, then utilize that y equals so that you can avoid some of those parentheses. Yeah. Okay, so 5/3 answer for number 3. You guys feel pretty comfortable using that formula? Okay, so let's go ahead and work on the rest of these for a little bit. And then once you guys feel pretty comfortable, we'll go ahead and we'll do the surface area formula. Today is a pretty comfortable day. Today's not a crazy day. Okay? All right. Okay. So previously in class, we would take a two-dimensional shape, right? We would take the area under a curve, and we would rotate it around an axis. And when we rotated it, it would create a 3D shape, right? And we would find the volume of that 3D shape, okay? Now, we're going to take that 3D shape, and instead of finding the volume of that 3D shape, we're going to find the surface area of that 3D shape. Does that make sense? So it's kind of like the flashback. This is where, if we had not had that snow day, we would have done that review lesson yesterday instead of the snow day when we ended up doing it. That's the context of what we're looking at here. So we're still taking those two-dimensional area underneath the curves, and we're still going to rotate them. But instead of finding the volume when we rotate them, we're going to find the surface area when we rotate them. Does that make sense? Okay. So surface area is 2 pi times the integral from a to b r, and right here we have 2 pi r. What formula is that? 2 pi r? Yeah, it's the circumference. It's like the perimeter of a circle. Circumference. Okay, 2 pi r. And then times 1 plus f prime of x squared dx. Okay, so r is the distance from the curve and the axis of rotation and it is always in terms of x. So if you can picture what this formula represents, it is the circumference of a circle multiplied by, what is this? What did we just find? The arc length. So circumference of a circle multiplied by the arc length. Okay, so let's go back to when we learned, we're picturing this would be comparable to a cylinder, right? Because we're dealing with circular objects because we're talking about spinning things. So if you had the surface area of like a cylinder object, you would find, like, think of a Pringles can. You would take like the circles, right? You'd have the circle for the bottom, the circle for the top, and then you'd have the can itself. We're still talking about the same thing. We're saying you have the circle, right, multiplied by the arc length. You guys see how it's kind of similar to that same idea? So, and because we're talking about integrals, we're talking about adding up infinitely many circles. Does that make sense? Because integrals is that limit as something goes to infinity, so that's adding up infinitely many. We've got slices of circles, slice, 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 and we're adding them up together. Does that make sense? Okay, so surface area, instead of adding up the volume of the circles, we're adding up the perimeter around the circle. That's why it's 2 pi r instead of pi r squared. Pi r squared would be adding up the area of the circle, which would be making a volume. You would do area of the circle times the length. we're not doing area of the circle times the length because we're not finding the volume. We're doing the perimeter of the circle times the length because we're finding the surface area. Does that make sense? Okay, and then we're doing integral because we're doing infinitely many. We want to find the whole thing. We're using calculus because we know that when we have a curve, it's not going to be like a Pringles can. It's not going to be a consistent circle all the way. It's going to be a changing circle. And so calculus allows us to do it with a changing circle. Does that make sense how that formula works? Okay. So we have two situations because we know that the R value, if it's going to be in terms of x, we know that's fine and dandy when you have a function that's in terms of x, but when you have a function that's in terms of y, that makes the problem a little bit more difficult, right? Okay, so we're going to say we have two situations. We have when you were rotating about the x-axis and when you were rotating about the y-axis, because we want to make sure that we know how to do this in both cases. So we're going to say, I'm just going to give you guys some theoretical curve here. So let's say this is what your curve looks like. So if you're rotating about the x-axis, you're rotating this way. And so then your radius, because that's what r is, it's your radius, 2 pi r, that's the radius of your circle. Then your radius is going to measure this way. This is your radius, radius, radius. So this is your radius. Radius, radius. So your radius would just be your y value, right? Because it's the distance from the bottom to the top. That's your y value. So your radius equals your y value, and we know y just equals the function, right? Y equals the function. So when you're rotating a it's really nice because r is just going to be literally the function. You're just going to take the function, you're going to plug it right in for r. Does that make sense? Okay. Now, if what I wrote here doesn't make sense, you can put some words down there and say, like, literally, if you're rotating about the x-axis, just plug the function in for r. Okay? So if the way I wrote it doesn't make sense, write it in such a way in your notes that it does make sense for you. Okay, over here, same sort of curve. If you're rotating about the y-axis, then you're going to be rotating this way. Now your radius is no longer y equals. Now your radius goes this way. So it doesn't correspond to the y coordinate anymore. Now the radius corresponds to the x coordinate. So here, the radius is just going to equal x. It doesn't equal the function. It literally just equals x, plain old x. So you are literally just going to write an x right there. That's all you're going to write. Not the function, literally just x. Does that make sense? Okay. All right. So now let's do some examples now that we have those two things figured out. So example 1. Find the surface area of the solid. Find the surface area of the solid formed by revolving f of x equals x to the third from 0, 1 about the x-axis. Okay. So we'll start off almost as though we're finding the arc length because it still has that same arc length formula in it, and then it has a little bit extra. So I'm going to start off just by saying, okay, I've got y equals x to the third, and y prime equals 3x squared. So I've got my function, I've got my derivative, because here I need my derivative for this piece. Okay? So now I can go ahead and start writing out my formula. Surface area equals, oops, I need my 2 pi first. Go ahead and write your 2 pi. 2 pi, and then my bounds are what? 0 to 1. And then for my radius, this one is rotated about the x-axis, and so my radius is going to be y equals the function itself. And so the function itself is x to the third. So I'm going to write x to the third. And then I can write square root 1 plus, and now I can do the derivative squared. Okay. How do you guys feel about that? Pretty good? Okay. So let's go ahead and type the whole thing in, see what we get. Now this one, we could totally have done this one by hand. This would have been a great u substitution problem. Because we could set the inside as the u, the derivative of the inside is outside. We totally could have done this as a u substitution problem by hand. That would have been a fair question to ask. But I'm not going to make you do that. Let's go ahead and just plug it in the calculator. So what are we getting? I'm not typing it in because my calculator is all the way over there and I can't reach it. Perfect. 3.563. Ta-da! All right. We got it? No, that's fine. You guys can be my calculators. That's cool. I feel like you guys are pretty good calculators. All right, next question, example 2. Find the area of the surface. Find the area of the surface when y equals x squared. Find the area of the surface when y equals x squared from 0 to root 2 is revolved around the y-axis. Okay. So we write down the function and the derivative of the function. So y equals x squared. Y prime is 2x. And the surface area is 2 pi r is just x. And this is another problem where if we could totally do this by hand if we needed to. This is one we definitely have just regular u substitution, we'd be able to do it. Perfect. Boom. Ooh, those are so fun. What a nice day when it's just simple formulas. One more thing to memorize, why not? That's what I say. Calculus, another formula? Shocker, you know? Okay, so that's all we've got for today. The next set of problems are, I don't know because I put them on the back wall. Let me look on Canvas.